Okay, morning class. I hope everybody is doing well. So we're going to continue to talk about the lecture for the polymer physics in terms of polymer solution. We're going to do something different with what we talked about Flory-Hagen theory, lattice theory. Speaking about those two theory, in the previous several lecture, we talked about them quite a lot. And I asked somebody I actually asked everybody to send in a quiz. In the last lecture, I didn't hear everybody. Some of you has already sent to me. I already gave back my feedback, and still half of the class is still need to send in the quiz. Okay, so if you have not sent in, it's likely that you guys did not watch the last recorded video. So please go ahead, do it after the class. What we have discussed in the last few lectures about how we can understand the solution phase behavior using the lattice theory, then later the Flory-Hagen theory. Those are very fundamental and very important for our field. And for today's lecture, we're going to talk about something different. Today's lecture, we're going to talk about let me first do one thing. I hear a sound whenever someone joins, so I'm going to turn that off. Okay, now we are good. We're going to talk about a related problem to Flory-Hagen theory, that is osmotic pressure problem. And this particular problem is also very important in the field of polymer physics. And we're going to go through it and discuss what is osmotic pressure, and how do we measure them, and why this matters in the polymer physics. Particularly, I want to discuss about how this osmotic pressure actually is related to Flory-Hagen theory we have discussed in the last few lecture. Okay. It may sound actually a little bit strange that why Flory-Hagen's parameter is related to osmotic pressure, but they're fundamentally linked. They are both thermodynamic parameters, and what you will learn from this is a process that related to how does a polymer aggregate, and how does polymer swell in the solution states, etc. So let's talk about it then. First is for the class, what is osmotic pressure at the first place? Can someone give me a good answer about what are these?
Can you hear us?
Yeah. Now I can hear you.
Okay. Osmotic pressure is just diffusion, pretty much.
Jalen, it's a very simplified answer, but why there is diffusion happening? Can you give a little bit explanation?
Concentration gradient.
Okay, very good. So let's talk about it in this particular scheme and cartoon. So you can understand this as a simple membrane-based osmotic pressure cell, and this is what I show here on the left and on the right. Those gray dots are representing the solvent molecular. So those are just the solvents swimming around, and those purple a bluish mesh is just the polymer coil by itself. So you can see we have assumed there's three coils. And if you somehow can put a polymer membrane, and the specific about this membrane is you can let the solvent go in through them freely, but not the polymer. So if we put a barrier here that allows polymer to stay on the right, then we would be able to see an interesting phenomena is that if we measure the height of the capillary on the top, it does not necessarily need to be a capillary, but it's much easier to see what's the height difference here. So in the experiment, typically people explain this on the context capillary, where you can see there is a certain liquid going to reach a height of, let's assume it's L, and on the right hand, this liquid going to reach a little bit higher in height. And this height difference as you know, the height can be translated into the pressure, because the higher the liquid, the more pressure is given at any point inside the solvent. So raise in the pressure on the side 2 is basically can tell you what is osmotic pressure on the polymer side. Okay, so in the case we show here, that's the yellow parts, that's where you have additional solvents present in the height. This will depend on many factors. This raise in the polymer can depend on solvent quality, as well as what type of polymer in there, as well as how much a concentration in the polymer inside the solution. We actually will discuss in more detail. If you have difficulty visualizing or understand why this has to be raised, you can understand this in terms of the solvents on the left side, as the Jalen says, it has a defined concentration, right? So let's say this is going to be C0. On the right hand side, inside the polymer, the concentration is different within this polymer core as well here. So in order to make them have the same concentration, the solvent will try to diffuse to the right side to equalize the difference in this. Particularly, we call it the concentration gradient, or more technically, we call them chemical potential. So chemical potential is just talks about, think about it as also a way of energy inside, free energy inside a particular material system. If you have this particular chemical potential is equal on both sides, that means they will not have any exchange in energy. But if they were not, then you would likely to have inflow of energy or concentration or molecular until these two values are equilibrized. So this is shown in the bottom. When you have concentration differences, you have polymer on the right hand side, then chemical potential on the left for the solvents need to be equalized for the chemical potential on the right with addition of osmotic pressure term. So this is a fundamental of what is osmotic pressure and how do we understand them in the polymer solution. So next is we're going to discuss how does osmotic pressure depends on the Flory-Huggins theory. The Flory-Huggins theory actually talked about a lot about free energy delta G. Free energy is one of the driving force for you to understand if the polymer and solvent will mix or not. As you can imagine, if the polymer is well mixed with solvents, then there's going to be more, particularly these solvents want to go into the polymer to swirl them. And degree of swirling or how much rises of this osmotic pressure then would depend on the quality of solvents as well as your polymer, right? So this is the interesting fact that if you recall what we talked about in the Flory-Huggins theory, there's an entropy term and there's an enthalpy term. In the enthalpy term, we know that it describes what is the interaction between your polymer chain and your solvents. And we specifically use a parameter called the Flory-Huggins parameter that describes all the interactions between A and B. So using the osmotic pressure, I'm going to ask everybody a question. Is there a way we can measure Flory-Huggins parameter using the osmotic pressure? Do you think or believe there might be a way?
Yes.
Very short answer. So the purpose of this lecture is I will show everybody how they are linked and how can we use osmotic pressure as a mean to measure Flory-Huggins parameter. There's many ways you can measure Flory-Huggins parameter. But Flory-Huggins theory as well as osmotic pressure is a very simple and straightforward way. So let's go through the process, and we will also discuss in today's lecture how does chi parameter can be measured and how we can use this simple measurement to kind of experiment our Flory-Huggins theory. So before we do that, we're gonna talk one more turn about what is the osmotic pressure and how do we understand osmotic pressure using the thermodynamics. So we need to define actually one term is chemical potential. How do we define chemical potential? So there's still some formatting issue, but this particular term where I write in the box is basically the chemical potential. So what this says is delta G is the free energy. If you take a partial derivative with respect to the molar volume, and is how much moles of your solvent there, you can get a chemical potential. And we know the delta G, we can write a generic term as delta G will equals to minus S multiplied by dt and V multiplied by dP and chemical potential multiplied by dN. So this is another way what we can write in the more generically as thermodynamics of delta G. It will relate to STVP. PV is basically pressure, talked about volume change and how much work you can had related to the volume.
Professor, I don't know if you can see the chat right now, but a lot of us can't see anything on your slide. It's pretty blurry again.
Okay. Let me see what I can do. That's a very good point. We can do two ways again. I'll try to zoom in, see if everybody can see it. If it's not, then I'll figure out a better way to show those tiny texts. Is it better now with respect to using this way?
Yeah.
Barely or
after the P, are those N's or R's?
After the P is there? Yeah. It's Ni not equals to Nj, and those are N basically with respect to the partial molar volume. I also recommend the other way we can actually address this problem is everybody have access to the canvas?
Yes.
Okay. The second route, if you have a problem, is download the PowerPoint slides, and you can go to the exactly same slides. And if you need some more time to review that particular slide, just let me know. That way we could also help you guys to see if you cannot tell what number is on the screen. Okay?
Sure.
Okay. So let's continue. I'll try to slow down, and whenever you have a question regarding the equation, feel free to stop me and ask me about that. Okay? So what we talked about just a minute ago is just what is the definition of Gibbs free energy and how we can define it in terms of entropy and temperature, pressure versus volume. dP is pressure, V is volume. So if you learn the second law of thermodynamics, so these are basically a very generic way you can write what is a free energy in terms of material system. So therefore we get a few relationship as shown here, and this is nothing fancy. Basically it says, let me again zoom it in. Delta G, take a partial derivative into the temperature if we assume P is constant and Ni not equals to Nj. There is a displays issue. Nj, then you would equals to minus St. It's very straightforward. How do you understand it? If we fix P and N, that means we're going to take away the second term and take away the third term. So if you take now a partial derivative with the temperature, you would equals to minus S is what is what this particular says. And you can do the same to understand what is the definition of partial derivative in terms of molar volume. Then you would get what is the chemical potential. Using that, we can understand in the context of today's lecture. Let me address this one moment. today's lecture, if we take partial derivative of chemical potential with respect to the pressure, we can reach a conclusion that we would equals to partial derivative of volume derived by the molar volume. And in the process, what happens in the middle is that we basically expanded what is chemical potential divided by P, because chemical potential is equals to delta G divided partial derivative of Ni. And now we switch to these two terms in terms of which one we go first. If we take the partial derivative with P, then with N we get chemical potential. But if we take chemical potential with partial derivative as pressure, we would get volume. You get volume, then you take a partial derivative with Ni. That's what we are trying to do here. And this is basically the definition of partial molar volume. What partial molar volume is basically tell you how does the volume and dependence on the different molar. And this is important, as we will show in the next slides. And I'm going to zoom in again. As we know, in terms of membrane, in terms of cell, what drives the chemical potential difference is basically how much delta G with respect to P on both sides. So on the right side, we need to consider the presence of the polymer in the solution. But on the left, we don't. So we just need to think about where the these solvents. And when there is no solvents movement, that means chemical potential for the solvents will be equal. Okay? So this means chemical potential will be equal on the left and on the right side. And basically what we wrote here, chemical potential for the solvent on the right hand side at a certain temperature and a certain pressure, T and P, will be equals to the chemical potential on the right hand side as TP and plus osmotic pressure. With that, we now can discuss how we can understand those. So by expanding this particular equation, we can reach out to a conclusion that your chemical potential on the right will need to be equal to the right, left you need to be equal to the right for the solvents. We can expand on the right hand side where you can get chemical potential plus the osmotic pressure. Osmotic pressure is defined as this chemical potential take a partial derivative with pressure and multiply by dP. Okay? So with that, you can reach out to this particular relationship where chemical potential would be equals to left side will be equal to right side multiplied by chemical potential and VI. VI is the molar volume. Okay? So if you do a little bit discussion, we will see that delta G for the ideal gas, you can also write as a dimensionless number as this particular A term. This is a dimensionless number. What this means is there is not a unit there, it's just a constant number. Okay? With that, we can shuffle a little bit. So what we need to get is this osmotic pressure term. So we're going to move this chemical potential term to the left and reach as equation as shown as below. And what you also need to pay attention to is mu1, mu2. You can further simplify this equation to down here, where chemical potential pi multiplied by V1 will be equals to minus RT log x1. x1 is a volume fraction for the minor phase. So this now gives us an opportunity to further test our Flory-Hagen theory. So how does this work? So this particular term, we can use a Taylor expansion to expand it. As x1 is a volume fraction for the solvents, and we can write as x1 would be equals to minus x2. This would be the volume fraction of your polymer. Then you can do a simple expansion as shown in here in the bottom, where osmotic pressure divided by RT will be equals to, this will be x2 divided by V1 plus AX2 square plus AX2 cubical and plus higher volume term. So one thing that I want to help everybody is, this looks like some of the numbers are shifting around and doing weird stuff. Let me write again in the bottom so that everybody can see what is. Pi divided by RT will be equals to x2 divided by V1 plus A2 x2 square plus A3 x cubical, and now you can have higher order term. So A2, A3, what are these? A2, A3 are just two constants. We define them in the field of the polymer physics. We call them second and third viral coefficient. So as we show here, this would be the third, and A2 would be the second. Okay, so these are defined as here. What these means is they are just a constant. We don't know what the physical meaning of it, so we just write them as A2, A3. And later I will explain A2 actually is well related to the Flory-Huggins parameter, and we can basically use A2 to understand what's the chi value for our polymer. And X2 is basic concentration of the polymer, right, as we already know. So what you can do now is very simple. To measure osmotic pressure, pi, with respect to the X2. And this is, in the later part we're going to show, what you need to do is to prepare a polymer solution at different concentrations. So let's say I made a 1 mg per mil and 2 and 3 and 10. Then I measure osmotic pressure, what the pressure is present inside this particular concentration. And how do you measure pressure is basically by measuring how much raise in terms of your capillary tube, as shown in top right here. Okay. Nowadays, this is a very old way, and nowadays you have modern instrument can measure osmotic pressure for you. What we could also link is when we can measure the weight fraction that X2 or into volume fraction into the concentration, right? So you have a certain volume fraction, let's say 1% of polymer in solvents. You can, if you know the molecular weight of the polymer, you can convert that volume fraction to the weight fraction. Weight fraction is mg per mil or concentration, okay? And this is what we're gonna do here. We're gonna link the X2 to C2. X2 is basically the volume fraction, and C2 is a concentration. And this can be basically done using a simple transition between the mass and basically with respect to the volume. So C2 would be equals to N2 is how many moles of your polymer multiplied by N is basically your molecular weight, and divided by V1. V1 is a concentration, okay? So you can simply rearrange to get what is relationship between the N and the C. And we can further use what we know previously, what is the concentration into the molar volume. X2 is going to be equals to N2 divided by 1 plus N2. N1, N2 is total volume, total molar volume, total mole of the solvents and solute, and N2 is basically how many moles of polymer. You adding them together and use N2 divided by this, you can get X2. X2 in this case, let me remind everybody, this would be the molar volume, okay? So example would be if you dissolve 1 mole of polymer in 10 moles of solvents. So this will be equals to 1 divided by 1 plus 10. This will be about 9% in terms of molar volume. And you can use 9% of molar volume to convert to concentration, right? 1 mole of your polystyrene, for example, multiplied by molecular weight of polystyrene, you can get how many grams of polystyrene divided by how much volume in terms of solvents you have. This is basically what we can show in here, what it would be X2 relate to C2. And we're going to do one more thing is to change the X2 now conversion into C2. And I'll explain in a minute why we need to do that. Because in the very simple and beautiful equation shown here, we still have a V1 term. It's not an easy measurement for this particular term. However, if we add in these X2, convert them into the concentration, we can reach out to this very simple and beautiful equation for the osmotic pressure. So this equation in the yellow box tells you osmotic pressure divided by RT. R again is a gas constant, T is temperature, will be equals to C is the concentration of your polymer in solution. So if you divide it, if you prepare something, you can easily calculate like how many milligrams per mil. Okay, if you have 1 grams per mil or 10 milligrams per mil, whatever you want to prepare. So this would be the C, and M is molecular weight. And we will see the other thing that osmotic pressure is very useful is to determine the molecular weight of your polymer. If you replace these, particularly those terms, you will see the V term can be cancelled out. So you no longer have any V terms in here. And additionally, we still have the second variable coefficient. So this is defined as A2 and A3. So what this means is osmotic pressure will be dependent on the concentration. It's very clear. You have C everywhere. And typically concentration is low. So the higher the exponent you have on the concentration, that means there's not much dependence here. Like if your concentration is 0.01, if you take a cubic, this term will no longer matter. Same for even higher term. Okay? So in reality, what really matters is usually just those two terms. And that's why the second viral coefficient is way more important than the third viral coefficient. And typically people don't talk about this A3 term anymore. And what is important is what is A2 term and how does osmotic pressure depend on concentration and molecular weight. So in this case, we're going to talk about how they would be dependent on these two terms. Okay. Of course, some of the researchers found that you can also rewrite this equation, particularly if you divide a concentration term on each side. If you divide a C on the left part of the equation and the right part of the equation, you can rewrite the same equation to this. Now you can see you have an additional C term, concentration term on the left, and you have second variable coefficient is only depend on C, but not the C square. On the left, if you pay attention, this is still the C square term on the left. So why this is also very important? This form is often more used because it is more practical and simple to interpret the data. As I mentioned, experimentally, how you have a way, how you can measure how does the concentration dependence, right? So you can prepare different solvents and concentration on polymer in solution and measure their osmotic pressure. So on this side, what you need to do is, again, quite simple. You measure different concentration, you measure different osmotic pressure. Then you just plot osmotic pressure divided by CRT term and see how does the data look like. So now you can see if we omit the high order term and we only consider these two terms, what you will see is 1 divided by molecular weight will be a constant, right? If you know the molecular weight of your polymer, no matter how much concentration you put there, and molecular weight won't change. So you always have a constant term. And A2 multiplied by C is a linear fit to A2 term. So if you can plot everything on this as Y equals to pi CRT, X term as a concentration, you would be able to get a YX plot, and we'll intercept with a y-axis, and this intercept is basically will be 1 divided by m, and using that you can calculate what's the molecular weight, and you can also see the slope of this will be the A2, and you can use this way to calculate A2. I'll go talk a little bit more detail. So what is a second and third vary coefficient in this particular case? So what this means is basically your second vary coefficient A2 is going to be related to two body interaction, one molecular interaction with solvents, and A3 is basically higher order of interaction. If you have 3 components inside the polymer, how do they interact with each other? This 3 body interaction can cover polymer solvent interaction. And if you look at what is A2, it describes polymer molecular and solvent interaction. And if you're paying attention to what is the Flory-Huggins theory, in the kite parameter we discussed, it's also the interaction between just a solvent and a polymer, right? It's the same two-body interaction. And you're describing the same interaction between 2 species, just water, not necessarily water, but the solvent and the polymer. Okay? So, but I will remind you that it is slightly different between what is A2 and the chi. I will describe in later part how do they relate. So A2 will be equals to 1/2 divided by chi, minus chi. Okay, so A2 is equals to 0.5 minus chi. That's how these two parameters are actually linked. We will go through a few more mathematical calculation to link these two together. But for now, what you need to know is equation here. And how does this will be relate to what is chi parameter? If we remember what we said, the chi is bigger, that means they are not likely to mix. That means you would likely to have bad solvents. So this applies to here. When A2 is negative, that means the more polymer you put in the solution, the osmotic pressure actually drops. That means you have a poor solvent. The chain will collapse and precipitate. If you have a good solvent, now you would have this A2 term or this particular slope. So if you look at this, if the A2 term is a positive slope, in this case, it will increase with concentration for the osmotic pressure divided by CRT, then this tells you have a good solvent. The more polymer you put there, the more osmotic pressure you can measure. Of course, this is also possible you can have a negative term, right? And if that's the case, if you have poor solvent, let me find a space just right here, then when you put in pi, osmotic pressure divided by CRT, if you put in more polymer chains in it, your osmotic pressure unfortunately will drop and start to have less and less osmotic pressure. So with that, we're going to look at some of the data where you can actually see the A2 term or the second vary coefficient can be swing between negative to positive at different temperatures. So this plot is A2 term. Okay, this is A2, the second vary coefficient. You can see we covered negative value minus 3 to 0 and positive value from 0 to 2. And you can see that this can be negative. That means your polymer is poor solvents. And you can have A2 as positive value, which means it's good solvents. And this applies to this material system. If you change the temperature, it will have a dependence on it as well. So, and you're probably curious, what's the physical meaning of A2 if it's 0? That means no matter what you add it, change the concentration, the Florey-Huggins, the A2 term does not change, or the particularly the osmotic pressure doesn't change. That's a very special condition, as we talked about in the first chapter of the polymer physics. This is equal to the Seda solvent condition. And if everybody recall what Seda solvent basically says, your polymer chain will adopt an ideal chain configuration. That means there's it follows ideal Gaussian chain, and there's no expansion of your polymer chain. And now you have a way to know if your polymer is in the Seda solvent or not. That is through the second vary coefficient and osmotic pressure measurement. It's a very special case where, as you can see, the osmotic pressure is not dependent on concentration. Okay, so is everybody clear about what the physical meaning of second vary coefficient and three special case for A2? When A2 is larger than 0, A2 equals to 0, and what is A2 negative? Okay, can everybody understand that?
I have a question, sir.
Sure, Brian, please.
You mentioned that A2 was more important than A3. Is that because it's more likely not, for all intents and purposes, we're only dealing with polymer solution interactions, or was there another reason?
Very good question. So Brian asked in the expansion why we only discuss this A2 term but not A3 term. And as I explained, A2 is just a polymer solvent interaction. Well, A3 is more like three-body interaction where you have multiple either polymer-polymer solvents or polymer solvent-solvent interaction. Why A2 is more important and more prominent? When you have three-body interaction, you need to consider the concentration of cubicle. Okay, so C is cubicle, and if you check what does A2 and A3 differs, is A2 is dependent on only two body, so you only need to consider concentration twice, or C cubicle, C square. Okay. And that makes a huge difference, because a lot of time we will not be able to prepare a very concentrated solvent, a concentrated solution to measure osmotic pressure. It's typically done in dilute solution condition. And in the dilute solution condition, your C is going to be very small, right? If you talk about dilute concentration C is typically 10 to the minus 2, 10 to the minus 3. If you take a cubicle versus a square, you will see A3 term will be not making a huge impact, because you have additional C3 term there, and it's likely going to be very little. And if you consider full body interaction, will be also exist in the solution, and it will be even smaller. Okay. All right. Any additional question?
Hey, I have been losing connection here and there, and I just got connection a minute ago. What was A2 equals 0? What was the situation that was going on with that?
Very good question. So James, A2 equals to 0 will define the polymer is in a Seda solvents. Okay, that means polymer will adopt the ideal Gaussian chain configuration.
Okay, thank you.
You're welcome. So All right, I want to go into this particular curve. So how do we use osmotic pressure? And this is a great example where we discuss how does osmotic pressure experiment is actually done and used. So if I made a new polymer and I dissolved them in a certain, let's say I made a fancy new polymer in our lab. We call it polymer X, and we don't know what it is. And we want to know how does polymer X is dissolved in solvent, toluene, hexane, and let's say chlorobenzene. Are these good solvent or not? And we now have a way to do it. And what we're going to do is to get a student to prepare those solutions in different concentration C. You weigh your polymer and you can now dissolve in those solvents and at different concentration. 1 mg per ml, 2 mg per ml, 10 mg per ml, etc. You need to get a couple concentration. You put in these osmotic pressure measurement instrument and you measure what is osmotic pressure. And pressure is just a term where you can get in the Pascal. And we will see that some of the homework we actually discussed and talk about this osmotic term. And they would just tell you the polymer, the concentration, and osmotic pressure. And how do we use the data? So what we need to do is to calculate what's osmotic pressure dependence on CRT. So this osmotic pressure is measured by the instrument, and this CRT is calculated for each sample. You would be able to plot the data as I mentioned in the previously, mx plus b term, and get this particular term. And let me remind everybody, please pay close attention to the axis. This is not the pi RT, okay? It's not. It's actually pi divided by CRT. And C is concentration. So you need to normalize by concentration first, then make this plot. And as we know, the intercept will be 1 divided by n, and slope will be equals to R2. Okay? You will have the opportunity to practice in the homework. And this is how we do it. So my student would be able to tell, is the slope going to be positive, going this way, or it will be almost flat, or it will be a negative value. And this will tell you how does solvent quality and how does it behave for the polymer core. And A2 is again also related to chi. If you know what's the A2 value, you can calculate chi using a very simple equation, 0.5 minus this A2 value. Okay? And a few examples where you can actually see that secondary coefficient basically can be measured and compiled. And here is a couple example polyvinyl butyrol can be discussed. Okay? Where you can see here where how their second viral coefficient is shown in this particular column. You can see this is positive, which means very good solvent. This is actually very little. 10 to the minus 4 is you can consider it's close to 0, or this is actually very low value. Okay. And here is another way you can see how the data is being processed and used. So let's use polystyrene cyclohexane as an example. And we know polymer in cyclohexane is a special condition. If you recall that in one of the homework, we know like polystyrene cyclohexane is at Seda solvent at about 34-35 degrees. And we will see exactly how this works. Okay, again, you're going to prepare different concentration. So this is concentration, and this is basically 0.01 grams per mil or 10 milligram per mil. You just weigh and how much you can have polystyrene dissolved in. You can measure them at different temperature. As we show here, we have 3 different temperature, and osmotic pressure is expressed in the Pascal or ATM. ATM is atomic pressure, and you can have that as a way to present it. As concentration goes to near to zero, this osmotic pressure will be zero. So this is experimental data you want to measure. But remember, I said at the beginning, if you want to use osmotic pressure to get molecular weight and second variable coefficient, you should not plot this osmotic pressure with respect to concentration. You need to convert this to what we call it osmotic pressure divided by CRT. This will give you a new plot as shown on the right. And concentration will be the same. You will still have same concentration as what you measured before, but now this linear increase into the osmotic pressure with concentration will be changed to the right, where you would see now we have three different slopes. You have a slope is positive for the polystyrene cyclohexane at 50 degree, and you have almost a linear at 35 degree, and you have a negative of A2 value at low temperature 20 degree. And what this means is polystyrene would show a good solvent inside cyclohexane at 50 degree, a Zeta solvent at 34.5 degree, and a bad solvent at very low temperature. Okay, and that's one thing. The slope, it tells you the solvent quality, and the intercept with here, where I marked as red dots, tells you what's the molecular weight. Okay, so this will tell you what's the molecular weight of your polystyrene, and you can tell this intercept is 5 multiplied by 10 to the power of minus 5. If you use 1, inverse that. If you use 1 divided by this value, this is about 20 kilodalton polystyrene, okay, or 20 mix per mil. So this is what people is using the osmotic pressure to understand the polymer solvent interaction, and also as a good way to get the molecular weight. So additionally, one of the contribution from the third variable coefficient, as I mentioned, in a dilute solution, it doesn't matter that much because A3 term is no longer very important. If you take a cubic of A3, this will be very little. No matter what A3 is, either is a positive or negative term, if you have concentration as it show here, 0.04, which means it will be 25%, it will be 4% of what is A2 term into the significance, right? But as you can tell, when the C is getting bigger and bigger, this will start to matter. And the question is, when does the third variable coefficient start to matter is shown here. When you have C approach as high as 1, then you will start to see your measurement will not be a linear term, and your curve will start to curve up because this cubical A3 term. And this only happens when your C is very high. As our data in the previous mini example, we actually only consider the data in the initial box when our concentration peaked at 0.05, right? So it's very little. And in this region, it will be pretty much linear data, okay? And that's why in a lot of time when you measure the osmotic pressure, people assume you're going to do it in a very dilute condition. You never want to exceed a very high concentration as an example of 1 mix per mil, something like that. Okay, 1 gram per mil. I think we're gonna actually end today's lecture right here, and in the next lecture we're going to talk about how does osmotic pressure actually is relate to the Flory-Hagen theory. It's going to be a very simple summary. And I'll leave the home everybody a short question to think about when you get home is how does A2 is related to chi? How can we get this relationship A2 is equals to half divided by chi from the Flory-Hagen theory? in up to now, we don't know they are connected. We only know briefly they both talked about polymer solvent interaction, but how exactly they are linked, we're going to discuss in the next lecture. I'm going to stop here, and anyone have any question about today's lecture? Feel free to ask now. We got a few minutes to answer your question. Okay, so looks like we should be good now. There's no answer any question yet. All right, then let's wrap up today's lecture. On this Thursday, we're going to continue to talk about osmotic pressure, and hopefully we can wrap that up. And in the next section, we're going to start to talk about the phase diagram. If we know the osmotic pressure, quality of solvents, and particularly one term that, as you can see, the quality of solvent in this depends on temperature. So that's a very interesting point, that your polymer can be in good solvent and can be in bad solvents, even with the same polymer solvent concentration and a pair, just by simply changing the temperature. And this is what we call the phase diagram. How do we know if you mix the polymer and a new solvent? Will they mix at various temperature? How do we predict it? How do we understand it? Is going to be the next topic, and we're going to go through the Flory-Hagen theory, revisit it, and predict something we call phase diagram. Okay, so with that, I'm going to wrap up today's class, and thanks everybody's attention. I'll talk to you guys on Thursday.
Okay, Dr. Gabe. Take care.
All right. Bye-bye, everybody.
Bye.